let's discuss about the concept of electrostatic potential energy in detail. Let us suppose that we are having a point charge. This is a point charge plus Q, and you know this thing that the electric field of the point charge is always radially outward. So these are the electric field lines, right? They obey the inverse square relationship also. We know this thing, okay? So suppose this is a line on positive x-axis, and suppose this is positive x-axis, and basically I would say that this is tending to infinity. This line is tending to infinity. Now the next thing is this, that let us suppose that we are having a charge here. The charge is plus Q. This positive charge plus Q is at point O, and this charge small plus Q is at the point P, right? As we know this thing that they both are having the same nature, right? Because if I'm not assigning the negative sign, it basically means the charge here is positive. So due to the charge capital plus Q, this charge will experience a force in this direction, and the force is nothing but equal to 1 upon 4 pi epsilon naught capital Q into small q divided by r square into I cap, okay? You know the formula. Distance from here to here is small r. Now the most important thing is this, that if the charge is displaced in this direction, so the work done by this charge, or I would say the work done by the electric field of this charge on this charge will be negative, because the force by the positive charge on a small q charge is in this direction and the displacement is in this direction. That's why this is happening, okay? So let us suppose that now my tendency is to move this charge along this direction, right? And if the charge is moving from here to here, let us suppose we are having an infinite seminal displacement, which is exactly equal to vector dr, right? Now dw is nothing but equal to vector f dot of dr, right? And this dw is due to this force. Remember one thing, work done is due to the force, and the force on this charge is due to plus capital Q charge. So you can also say here that work done is due to plus capital Q on small q. So instead of this thing, we can write 1 upon 4 pi epsilon naught capital Q into small q divided by r square dot of dr, and we know this thing that I cap dot of I cap is 1. So for this is the work done, okay? And you know very well, if the work done is positive, it basically means there will be the increment in the kinetic energy will increase. And if the work done is negative, it basically means the kinetic energy will decrease. One more thing is there, that this type of work done is actually the work done by the field, right? The electrostatic field, I would say, or this work done is nothing but the work done conservative. So you know very well that whenever there is a conservative work done, so there is a change in the potential energy. Well, there is a formula with the help of which we can correlate both of these things, that's the work done and the change in the potential energy. And the formula seems to look like this. If du is nothing but the change in the potential energy, infinite seminal change in the potential energy, so we can say this is negative of dw. Remember this thing, this actually is the conventional sign. Well, it depends upon the work done, that this work done is either positive or negative, so that we can have the positive or negative potential energy. Always keep this thing in mind. So you can observe in this scene that the charge is displaced from the point P to another point, right, in this direction. So we can say the work done is positive, so the change in potential energy will be negative. And you know very well, if the change in the potential energy is negative, so it basically implies that the change in the kinetic energy will be positive. So I would recommend to each and everyone here who is actually watching my lecture that always remember this formula which I am writing. Du is equal to negative of vector f dot of dr, okay? Du is equal to negative of vector f dot of dr, right? So it depends upon this, that this thing will be positive or negative, right? Remember this thing. Okay, now since the charge is displaced in this direction, so I'm now interested in finding out the change in the potential energy, right? Well, the change in the electrostatic potential energy, okay? Now, let us suppose that initially this charge Q was here at this position P1, And let us suppose from here to here the distance is r1. So let me write for you that this distance is r1, and finally let us suppose that the charge is actually at this point P2. This charge initially was here and finally exactly the charge was here. So we can simply say the charge is displaced from P1 point to P2 point, and this P2 point is actually R2 distance apart with respect to this point O. So what you can say about the displacement? Well, you can say that, sir, if the charge is displaced from point P1 to P2, so here the displacement will be, suppose delta vector R is a displacement, you can write this as vector R2 minus a vector R1, right? Or you can also say it as R2 minus R1 into I cap. Remember one thing, the force here actually depends upon the distance. So you cannot simply multiply force into displacement. Why? Because force is also changing with respect to distance. So we had to integrate this thing also. This is not a constant force. Whenever there is a variable, alright, this is a variable and this is changing with respect to distance. So basically means we had to integrate this r also. So what I'm going to do is, I'm taking this equation, putting the sign of summation. Well, this is the sign of integration, but I told you in classrooms also that sign of integration is somehow nothing but the sign of summation also, because it is summing up, right? It is summing up dr. Dr basically means infinite seminal displacement. So we are adding up in a continuous manner, we are adding up every dr. So that's why we are having this sign, right? Now dw can be written as, now instead of f, I'm going to write 1 upon 4 pi epsilon naught, and you know very well that capital Q and small q are constant, so they will pop out, right? And now I'm having here 1 upon of r squared dot of dr, and I hope you all know actually that the 1 upon r squared dr is having integration r ki power minus 1 upon minus 1. Okay, one more important thing also here is that if I'm leaving simply like this whole equation, it basically means we don't know actually from where to where actually we are moving this charge, small q charge. So by putting the limits, the lower limit and upper limit, we know actually from where we are displacing, from which position we are displacing the charge, and the charge will go to which position. So the most important thing is this, as you know this thing, that the displacement here is delta vector r for the given charge. So by writing here r1 and r2, we are saying to the integration that, look, we are integrating, or we are actually moving this charge from the point this to this thing. Okay, remember this thing. So whenever we are actually having the limits, it basically means we are defining something, right? So as we know this thing, that integration, let me write first of all this thing. So integration of 1 upon of r square is how much? Well, you can say, sir, this is r ki power minus 1, and minus 1 will pop out, right? No need to write like this, and instead of r ki power minus 1, I can write 1 upon of r. So we are having r1 here and we are having r2 here. Okay, so now this formula is for that of work done. Okay, and as we know this thing, that capital Q into small q divided by 4 pi epsilon naught, and by putting here 1 upon of r2 minus 1 upon of r1, we will have the work done. But by multiplying the equation, or I can say the part of the equation, by the sign minus, so we can write here that this will be 1 upon of r1 minus 1 upon r2. So that's the most important thing. So here you are getting work done to move the charge from the position P1 to P2, and the displacement here is nothing but equal to this much. Okay, that's the most important thing. So you can observe that since r1 is less than r2, this is less as compared to this, so this thing will be positive. So hereby, any of my student can say, we will have the positive work done. That's not wrong. We are having positive work done. Well, if you are interested in finding out the change in potential energy, what you have to do, you have to use this equation, or you have to use this equation. Simply, we had to put up here the sign of integration, sign of summation also, we can also say. Because one of my teacher who was actually expert in mathematics told me that this is somehow can be called as the sign of summation, and really you will have a deep feeling about the integration. Salute. So the most important thing is now we are going to integrate this thing, or we are going to integrate this thing. Whenever we are going to integrate this thing, so you can actually tell me that du will become as delta u. Remember one thing, whenever we are saying that du is u in physics, that's wrong, right? Well, du is infinitesimal variable or infinitesimal change in the potential energy, and delta u exactly will come when we are adding up, we are summing up all the du's. Okay, beta? So the most important thing is this, that here we will have delta u, right? So I'm integrating this thing, I'm having a delta u, and delta u is nothing but equal to minus w. So now you can observe one thing, and that is delta u. Now what is delta u here? Delta u is nothing but the change in potential energy. Let us suppose here the potential energy is u1. Let us suppose here the potential energy is u2. So you can simply understand that the change in the potential energy here is nothing but equal to u2 minus u1. And instead of this work done, you can write exactly this thing. This is work done. So you have to multiply this with minus sign. If you're multiplying this by minus sign, so you can say, sir, the equation will be like this: 1 upon 4 pi epsilon naught, capital Q, Q naught, small q. And after that, 1 upon of R2 minus 1 upon of R1. Now you can observe this thing, since R2 is more as compared to R1, so we are having here the negative sign. So change in potential energy is negative. Of course this is negative. I will tell you with the help of a practical demonstration, right? So if the work done is positive, the change in potential energy is negative. When the work done is negative, the change in potential energy is positive. Now let me tell you in a practical sense, how can we say this thing? I'm having a marker, I'm throwing, or I would say in other words that I'm giving the speed in this direction, that is j cap direction. I'm giving the speed in this direction. So this is going in upward direction and it is coming back. Imagine that this marker is going in this direction. And you know very well that the force due to gravity is acting in a vertical downward direction. So what will be the work done due to the force due to gravity on this marker? Well, you can say if the marker is displacing in this direction and the force is in this direction, sir, it basically means work done by the gravity or work done by the conservative force. Here this conservative force is nothing but the gravitational force is negative. And you are also observing one thing, and that is that if the kinetic energy is decreasing, of course the kinetic energy is decreasing, because you know this thing that this is actually one of the type of retarded motion, right? If the kinetic energy is decreasing, where the energy is going? We are having the decrement in the kinetic energy. Now where this kinetic energy is going? Well, the kinetic energy is stored in the system. It is hidden, or I would say the kinetic energy is changing. I'm very sorry for the light. It happens only in India, you know very well, right? What I was saying is this thing, that if there is a decrement or the kinetic energy decreasing with respect to the distance followed by the object, right? Where this kinetic energy is going? Well, this is actually stored up in the system in the form of the potential energy. And when the marker is coming back to the original position, you will observe that the potential energy is finally converted into the kinetic energy. So since the object is going in this direction, speed is decreasing, kinetic energy is decreasing. So which energy is actually increasing? Potential energy. And it is increasing by the same amount, by the amount in which the kinetic energy is decreasing. So that's the most important thing. So here also we are having the same case. If the charged particle is going in this direction, it basically means the work done is positive, or I can say the kinetic energy is increasing, and side by side potential energy is decreasing. So you can also say to me that if the charge is going in this direction, it basically means kinetic energy will decrease, of course, and the potential energy will increase. But let me tell you one thing, this will only happen when there is only force, when there is only one single force, due to this plus q charge on the charge small q. Is this clear? Otherwise, it may happen if this charge is under the action of another force, may be possible this cannot happen, which I told you. Okay, so this is the most important thing, that the work done, if is positive, then I would say that the change in the kinetic energy will be positive and the change in the potential energy is positive. So with the help of this formula, actually I told you about this particular thing? Well, now I would say that we are having capability to find out the potential energy. If we can find out the work done, then we can find out actually about the potential energy, or we can find out the change in the potential energy. Okay. Now the next thing, most of the students are saying, sir, that's okay, right? That we are not having any, let us imagine, no one is saying, let us suppose that some students are saying that's okay, that with the help of revealing actually the concept of the potential energy, electrostatic potential energy, we can find out, well, the concept of work done, we can find out the concept of change in potential energy. But how to find out the potential? Abhi, potential is not tough. If you can understand actually about the potential energy, change in the potential energy, then definitely actually you can also find out the change in potential. How? Like this. Let's take a case as an example. Suppose we are having a charge here, and the charge here is plus q, right? And let us suppose this is the line, right, about positive x-axis, and we are having some points. Suppose this is a point and this is the point. The name of this point is P1 and the name of this point is P2, and let us suppose this point is O, right? And now let us suppose that we are having a charge small q, and this small q is going from here to here. The distance from here to here is given. This is r1, right? And like the distance from the point O, let us suppose this is a fixed point, right? And the distance from here to here is actually r2. So the most important thing is this, that what will be the change in potential energy? That's damn easy. The change in potential energy, for example, will be equal to what? 1 upon 4 pi epsilon naught capital Q into small q in bracket 1 upon R2 minus 1 upon R1. Okay, you have to remember, you have to remember the formula, right? So this is nothing but the change in potential energy. Now, how to find out the change in potential, delta V? Somehow this is also called as potential difference, and somehow this is also called as voltage. When we will discuss the concepts of Ohm's law, so there in that topic, for the case of Ohm's law, we had to say it as voltage. V is equal to IR, is bar, Modi Sarkar, right? So basically delta V is nothing but the potential difference, or it can be called as voltage. So potential difference, or I would say the term potential difference came from the potential energy. You simply divide this whole equation by Q, right? By Q. Here also we will divide this by Q. Well, Q is this Q. So this is nothing but equal to delta V. That's it. Find out the change in potential energy. Divide by small q. You can find out the potential by this charge plus q at any given point. So now delta V actually is nothing but equal to U2 minus of U1 divided by Q. Okay, beta? Instead of delta U, I'm writing U2 minus U1 by Q. And now you know this thing that U2 is 1 upon 4 pi epsilon naught capital Q into small q divided by R2, and U1 is 1 upon 4 pi epsilon naught capital Q into small q divided by R1. Okay, so now this Q, we'll cancel this Q. So I would say that this is equal to 1 upon 4 pi epsilon naught capital Q, right? And in bracket we have to write 1 upon of R2 minus 1 upon of R1. Here we go. We are having the formula for the potential difference, and we can also write in this form, that is V2 minus of V1 is nothing but equal to this much, right? That's the most important thing. So now if you're asking that what will be the potential at this point, suppose this is general point, right? And suppose this charge is here. Let me tell you, if this charge is not here, then also this point will have potential. Potential or electric field is independent of another charge. If we had to find out the potential due to this charge here, here or here, there is no need to keep any other charge. So you can say, you can ask one question, that why we are then having this charge small q? For the sake of finding out the force, that's it. So with the help of the formula of force, right, Coulomb's law, we are able to find out so many things. Okay, so now the potential at the point P, suppose, well, distance from here to here is r, right? let us take, I'm sorry my dear, the distance from here to here is smaller. So the potential at the point P will be equal to 1 upon 4 pi epsilon naught capital Q by R. Easy, simple. I think there is no problem. So the potential energy here will be equal to what? Just multiply this by small q. Because if you are actually interested in calculating the potential energy, remember one thing, potential energy is a 2-point concept. 2-point concept means there should be interaction. You are listening what I am saying. And maybe possible you are also have the feeling now that yeah, this is actually the potential, this is potential difference, and all of these things are coming from the work done. So it basically means that we are interacting. Okay, so interacting basically means potential energy. But somehow if you're not there, but then also actually I know about the concepts of the potential energy of the work done. Okay, so I'm having my own potential in physics, but whenever you are coming, you are listening, so I would say that there is some revealing attitude you are having after learning. Okay, so it basically means we are exchanging our fields. Okay, so I would say that if the potential energy came, then definitely we had to keep this charge and this charge also. But for the case of the field and for the case of potential, only this charge will come, right? So the potential at this point P due to the charge here capital Q will be this much. Okay, so you can now take the screenshot of all of this thing. Now we will discuss about the electric field and the potential. So we are now having ability to make a relationship between the electric field and the potential. Okay, well, you know very well that dW is nothing but equal to vector F dot of dr. Well, you know very well this thing, right? I told you. And du can be written as negative of dw and negative of vector, negative vector F dot of vector dr. Well, this negative sign is conventional. I told you that if the work done is positive of this or this thing is positive, change in potential energy will be negative. And if this thing is actually negative or this thing is negative, so I can say this thing that the change in potential energy will be positive. Now, let us divide this whole equation by Q naught or Q, right? Hardly matters either you are taking Q or Q naught. But for the case of the previous concepts, we are taking the small q, and you know very well that du by q is dv, my dear, and simply minus dw by q, well, minus dw by q with the negative sign will be actually dv, and F upon of q is electric field, right? Force upon a charge. Force upon a charge is nothing but what? Well, this is nothing but the electric field. So this minus sign is this minus sign, minus vector E dot of dr. Here we go. So we are having another formula. This is a formula where dV is nothing but the change in potential, vector E is the electric field, and vector dr is nothing but the displacement. Okay. Now if you are integrating this thing, so you have to write delta V, and now by putting here R1 and putting here R2, and I would say that electric field is like this, vector E dot of dr. So finally I can say that the change in potential will be equal to capital Q upon a 4 pi epsilon naught in bracket 1 by R2 minus 1 by R1, right? I'm sorry. So this is nothing but equal to change in potential difference. So क्या था हमारा कॉन्सेप्ट इलेक्ट्रोस्टैटिक पोटेंशियल एनर्जी का, इलेक्ट्रोस्टैटिक पोटेंशियल का, इलेक्ट्रोस्टैटिक पोटेंशियल डिफरेंस का? पहले वर्क डन फाइंड आउट कर लो, ठीक है? अब तुम जानते हो कि जो वर्क डन है वो कंजर्वेटिव वर्क डन होगा, भाई ये निकालना आना चाहिए वर्क डन, फोर्स इनटू डिस्प्लेसमेंट, किसी भी इलेक्ट्रिक फील्ड की वजह से, किसी भी चार्ज की वजह से जो हमारा वर्क डन है उसे निकाल लो, चार्ज डिस्ट्रीब्यूशन है उसकी वजह से वर्क डन निकाल लो, ठीक है? हम लोग देखेंगे, वी विल टेक सम एग्जांपल्स, राइट? और उसके बाद में क्या करो कि वर्क डन जब निकाल लो उसके बाद में क्या करना है तुम्हारे को, देख लो कि वर्क डन पॉजिटिव है तो चेंज इन पोटेंशियल एनर्जी बाई नेगेटिव हो जाएगी, अगर वर्क डन एक्चुअली नेगेटिव है तो चेंज इन पोटेंशियल एनर्जी जो है वो पॉजिटिव हो जाएगी, ठीक है? अब बहुत से बच्चे एक्चुअली ये जो चीज़ मैंने बोली उसमें सोच रहे होंगे सर पोटेंशियल एनर्जी फॉर अ गिवन पॉइंट कैसे निकालेंगे, वो बात की बात वो देख लेंगे उससे, ठीक है, उसके लिए ज़्यादा टाइम नहीं लगेगा, एक क्वेश्चन के बेसिस पे हम लोग वो चीज़ कर लेंगे, ठीक। तो क्या कहा, फाइंड आउट द वर्क डन, वर्क डन का जो नेगेटिव होगा, नेगेटिव ऑफ वर्क डन अगर है तो चेंज इन पोटेंशियल क्या हो जाएगी, पॉजिटिव हो जाएगी। सिंपल बिंदास चेंज इन पोटेंशियल एनर्जी को चार्ज से डिवाइड कर दो, किस चार्ज से, दूसरे वाले चार्ज से, जिसकी वजह से तुम्हें पोटेंशियल नहीं निकालना है, ठीक है। चार्ज के आसपास फील्ड होता है, सो अगर फील्ड होता है उसके आसपास तो एक्चुअली हम ये भी बोल सकते हैं कि वहाँ पे मतलब किसी भी जगह पे एक्चुअली पोटेंशियल भी होता है। तो मैंने आपको एक और चीज़ बताई इस लेक्चर में, और वो ये था कि अगर हमें पोटेंशियल निकालना है या फिर एक्चुअली फील्ड निकालना है तो जरूरी नहीं है आप दूसरा चार्ज वहाँ पे रखो, फॉर द सेक ऑफ द फोर्स एंड फॉर द सेक ऑफ द वर्क डन और द पोटेंशियल एनर्जी वी हैव टू टेक एटलीस्ट 2 चार्जेस, सो दैट्स द मोस्ट इंपॉर्टेंट थिंग। सो आप देख रहे थे चेंज इन पोटेंशियल जो मैंने निकाला था उसमें क्या किया था, चेंज इन पोटेंशियल एनर्जी अपॉन ऑफ चार्ज कर दिया था, तो सिंपली एक्चुअली चेंज इन पोटेंशियल हमारा आ गया, बस यही है। अब जो नेक्स्ट लेक्चर मैं लूँगा राइट, तो उसमें एक्चुअली हम क्वेश्चंस करेंगे और ये देखेंगे कि जो हमने कॉन्सेप्ट्स करे हैं अभी, क्वेश्चंस को किस तरीके से सॉल्व किया जा सकता है। तो नेक्स्ट हमारा जो भी होगा, जो लेक्चर होगा, उसमें हम लोग जो है इसके बेसिस पे पोटेंशियल डिफरेंस, पोटेंशियल कंजर्वेशन, मैकेनिकल एनर्जी प्रिंसिपल भी एक्चुअली वहाँ पे लगा लेंगे, जो कि इसी से आता है, इन्हीं कॉन्सेप्ट से एक्चुअली निकल के कॉन्सेप्ट आता है। सो हम क्वेश्चन सॉल्व कर लेंगे। थैंक यू वेरी मच फॉर वॉचिंग द वीडियो।